Rock and roll. Welcome back to the second half, or welcome to the second half. Welcome back to the Big Data Conference, day one. Our first speaker for the afternoon, or again, whatever part of the day cycle you're in worldwide, is Nicole Immorlica. She is a senior principal researcher at Microsoft Research. Previously, she taught at Northwestern University. She's a highly honored, person. She's received the Sloan Fellowship, the Career Award, from the NSF, and a number of other accolades. She also, so we started the first session today with a force of nature. She is another force of nature. So she has held, so many leadership roles in the Econ CS community. I couldn't actually sort of put together a meaningful count. But recently she was program co-chair for the 20th ACM conference on economics and computation, and, sort of co-ran the digital, edition of the conference this year, sort of from nowhere, when we had like many conferences, including this big data conference to suddenly digitize. And I've worked with her for years, first as a, co-author and collaborator, and now sort of in SIG-Econ leadership. She's the chair of the special interest group on economics and computation, SIG-Econ, and somehow manages to find the time to be vice chair of a different, special interest group at the same time, SIG-Act. I can tell you, she is completely extraordinary, as a scholar, a leader and a person, and we are very excited to have her here to tell us about incentivizing exploration with selective data disclosure. Let's welcome Nicole.
Thank you for that introduction, Scott. And just to make sure you all realize how amazing Scott is as well, he is the vice chair of this SIG special interest group on economics and computation, SIG-Econ, which he mentioned. So we are both very busy making this field strong and awesome, and you should definitely consider joining our email list and coming to our conferences. So little shameless plug. Yes, thank you. So I'd like to talk to you today about incentivizing exploration with selective data disclosure. This is joint work with Jiming Mao, who is currently at Google Research. He was an intern at Microsoft at the time. Alex Slivkins, who's my colleague at Microsoft Research, and Stephen Wu, who is transitioning from University of Minnesota to CMU and was a postdoc at Microsoft at the time. So in incentivized exploration, agents are going to sequentially choose actions, and then they receive a stochastic reward from some unknown distribution. Some examples could be buying products, where agents are going to sequentially buy a product, say something like a car that you maybe buy pretty infrequently. When you buy the product, you receive a reward, which is related to the quality of your choice. Perhaps Toyota is a better car than Ford or something like this. And so your choice of which product to buy is influenced by your beliefs about the quality of the product. And this quality is a common value across all the agents in the society. Another application might be choosing medical treatment. So you contract a rare form of cancer, you need to figure out what medical treatment to undergo, and the quality of your choice, the reward that you get is the health outcome that your choice induces. And so in these kinds of settings, you might have these choices being coordinated by a principal. And so I'm going to be particularly interested in that setting when the choices of the agents are coordinated by a principal. And such a example that you might want to have in your head is that of a recommendation website, like say Yelp. So Yelp is going to recommend to agents restaurants that they might want to visit in different cities. Here I did a search for pizza in Greenwich Village, which is near where I live in Manhattan. And it returned a ranked list of options, including Arturo's, which it ranked first, which had 678 reviews and 4 stars, and Prince Street Pizza, which it ranked second, which had 4.5 stars, 3,463 reviews, and the list went on. And so Yelp is trying to help me select a pizza restaurant of a high quality. Maybe I'm a tourist, I'm only going to eat there once, so I need to find the best pizza restaurant available to me. I look at the information Yelp gives me, I pick a restaurant, I receive some reward from eating there, which is the quality of the pizza they serve. Then I, leave a star rating and a review and move on with my life. And the job of Yelp is to coordinate these choices of all of these restaurant connoisseurs in order to help them converge on a platform with a restaurant with high quality. And so in service of that goal, the principal, Yelp in the previous example, would like to encourage agents to explore, that is to take infrequently selected choices in order to learn more about them. And simultaneously, the principal would like to exploit in order to, because exploitation maximizes today's welfare. So it needs to trade off, find an optimal trade-off between this exploration and this exploitation in order to maximize the welfare in the long run. And the difficulty of this is that while the principal wants to both explore and exploit at some optimal rate for each type of action, the benefits of this exploration are only accrued by future agents and not by today's agent. And since these agents are short-lived, this results in misaligned incentives. The agents would rather exploit, each individual agent would rather exploit because exploration is only valuable down the line. So prior work tried to bridge this gap between the differing objectives of the principal and the agents by leveraging information asymmetry or payments to induce the optimal amount of exploration. In today's work, I am also going to leverage information asymmetry to induce exploration, but I'm going to do so in a restricted space, message space for the principal. So the principal, the platform, is going to be allowed to look at all past reviews and select some subset of them to display to the current agent, the current consumer. And this selection process, which I call selective data disclosure, so this disclosure policy should be a function of not of when the agent arrived. So, I know that the agent arrived, say it was the 10th agent to arrive, but it should not be a function of what the reviews said. So I have to decide upfront as Yelp that every 10th agent is going to see the same set of reviews, the reviews of all agents, all 10, X mod 10 agents. Then the other thing I want to assume in this model is that agents are going to be frequentists. So traditionally, we might assume that agents have a prior and that they do some Bayesian updating and then they take an action with the highest expected mean reward. Instead, I'm going to assume that agents are what I call frequentists. These are behavioral agents that are going to choose actions based not on some posterior that's computed from a prior, but rather as a function of the empirical mean of the data set and the number of points in the data set. So they're presented with some data set that includes a lot of past reviews, so the star ratings of all these past reviews. They look at the empirical mean, which, by the way, is prominently displayed in platforms like Yelp. And they look at the number of reviews that were used to compute that empirical mean, which again is prominently displayed in platforms like Yelp. And then they make an assumption about the reward of the arm. And I'll describe exactly what constraints I place on this assumption that they make. And then they take the arm which they assume has the highest mean. So this is the model, and I'll define it in more detail later. And then the results that we have in the context of this model are a simple policy that divides agents into focus groups and collates their data to get low regret with respect to the optimal reward. And then an optimal policy that leverages some additional features like group level aggregators and interlacing to reuse information in order to get an optimal, like the agents to learn at an optimal rate, provably optimal rate. So let me outline the talk for you. I'm going to discuss a bit of background, then some prior work. Then we'll go into the model and preliminaries. I'll define the setting more precisely mathematically. I'll show you the simple policy and give you some hints as to the construction of the optimal policy and then conclude. So the background, if you are at this conference, you've probably already noted that this problem I've stated sounds a lot like multi-arm bandits, which is a prominent problem in the machine learning and statistics literature. So in the multi-arm bandit problem, it's exactly like the incentivizing exploration problem, except that there are no agents. There's just a centralized planner. And this centralized planner sequentially chooses actions, receiving a stochastic reward from an unknown distribution as before, and is trying to maximize the sum of rewards that she receives. And this has been heavily studied because there's a ton of applications in computer science and more broadly, but some of the applications in computer science include things like online ad placement. So where on a web page should I place an ad? And the different placements are the actions I could choose. And my reward is one if the ad was clicked. Or algorithmic tuning, where I need to pick the parameters of an algorithm in order, like say some heuristic, in order to get the optimal performance from it. And if you are curious to know more about this literature and need a nice introduction, I highly recommend this book that was just published by my co-author, Alex Lifkin's Introduction to Multi-Arm Bandits. I think it's a really nice, gentle, and insightful introduction to the topic. There are some other great textbooks out there as well, but I have to be partial to my co-author, so I recommend that book. Okay, so what is the multi-arm bandit problem? Formally, I'm given actions, and in the multi-arm bandit problem, these are typically called arms. I'll probably switch between these two terms inadvertently throughout the talk. I mean the same thing. You have some time horizon t, and the planner chooses one arm in each time step, and then the arm yields a reward from an unknown distribution. The unknown distribution could either be drawn from prior, so in Bayesian bandits, the planner knows a prior over the distribution class, or it could be unknown, as in the case of stochastic bandits, which is what I'm studying today. The assumptions in this problem are that I'll be making, although you could have, again, people have studied relaxations of this as well. I'm going to assume bandit feedback, which means that you only see the reward of the arm that you choose, but you don't see what reward you would have gotten if you chose a different arm. And I'm going to assume IID rewards, which means that the rewards are drawn independently from a fixed distribution that depends on the arm, but not on time. The goal of the principle in the multi-arm bandit problem is to minimize regret, which is defined as the difference between the reward of pulling the optimal arm every time step versus the reward that the algorithm receives, summed up over the time horizon t. And one of the classic theorems in this literature is that for stochastic bandits, the optimal regret is something like root t. So I'm hiding some log factors here and some constants, but you can think that the best possible rate at which people can learn is something like square root of the time horizon. And things to note is that this convergence, this regret, is sublinear in time. So we get convergence eventually to the optimal policy. And this is robust in the sense that I approach this reward that any Bayesian planner would have without using any priors. So returning to the motivating example of Yelp, a clear distinction between the multi-arm bandit problem and the incentivizing exploration problem is that the planner can't pick which restaurant I go to. The planner has to take into account the incentives of the agents that are the ones that get to choose which arm to pull. So how does prior work manage to get agents to pull suboptimal arms in order to allow for exploration? And so the answer is that we can leverage the information asymmetry of the setting in order to convince agents to pull potentially suboptimal arms in some rounds. The idea is that only the principal knows the rewards of the past arm pulls, and so this information can be exploited. And for example, the principal might recommend exploration with some small probability and otherwise recommend exploitation. And since the agent doesn't know which arm is an exploration arm versus an exploitation arm, if the probability of an exploration recommendation is small enough, the agent is incentivized to follow whatever recommendation the principal provides. An alternative that's been looked at, although I won't get into it, is to pay agents to explore. So you can just compute how much they're losing by exploring and you pay them to do that. One thing to notice about this setting, this especially the first one I discussed, is that the principal doesn't give the agents any explanation. They simply say, you should pull arm A. And of course, the policy of the principal is set up such that this is going to be Bayesian incentive compatible. The agents are encouraged to pull arm A and want to pull arm A because of the mechanism, the policy that the principal has committed to. So the principal is commits to this signaling scheme. Agents sequentially choose arms based on the prior, and then without loss of generality, as I discussed, we can assume that the agents are going to just follow the recommendation that the principal states because the principal is committing to a BIC policy. And the really cool thing about this literature is that we can match the optimal regret rates for multi-arm bandits, even in the presence of incentives. So these papers and many follow-up works give schemes that get this regret rate of root T. There's some differences in the constants. In particular, these schemes are exponential in the number of arms, whereas when you have a centralized planner, you can make do with polynomial in the number of arms. But but basically, the parameter that grows without bound, T, is optimal in these constructions, which is pretty impressive. But there's some issues you might take with the constructions. One is, are these priors correct? So this is relying on agents having a prior, doing some Bayesian update, and then because it's in their best interest, then following the recommendation. So this relies on us assuming that the priors are correct and that agents are doing Bayesian updates appropriately. And the other is the commitment that it requires of the principal. So the principal has to commit to this small probability of recommending exploration. And so is it reasonable to assume that the principal has that commitment power? And even if the principal does have commitment power, can we assume that the algorithm that the principal implements is implemented correctly? On top of that, is it feasible? There's a lack of transparency here that I think would be fairly problematic in the actual environment. Is it feasible to just produce a single recommendation with no justification? And so the point of our paper is to make alternate assumptions instead of the assumptions of prior work. Instead of assuming Bayesian rational agents, we're going to assume that agents are frequentists. As I mentioned before, this means that they make inferences from empirical statistics of the data sets they are presented. We're going to assume that the signals are subhistories. So instead of having some complicated algorithm that produces some recommendations, the algorithm simply commits to revealing the data of a subset of the past agents. This is arguably more auditable if it were necessary to audit these websites. We are, in the context of this model, going to study stochastic bandits, as some of the prior work did, and show that with a simple scheme, we can get sublinear regret, which is going to be T to the 2/3. And then using a layered scheme, we're going to get optimal regret, which is, as I mentioned, root T. So that's the optimal regret, even in the absence of any incentive constraints. And the main idea, there's sort of three main ideas, but the simplest takeaway message is that you can achieve sublinear regret by grouping agents into focus groups, such that you get independent experiments in each focus group that then induces, because of the stochasticity of the rewards, sufficient exploration for the future agents to efficiently exploit. So there's a bunch of related work, which I don't have much time to get into, but in the information design and Bayesian persuasion literature, and you can think about this problem as sort of a repeated Bayesian persuasion game. So in that literature, people have looked at policies with restricted strategy spaces for the principal, which is essentially what I'm doing here. Then this is also related to the literature on hard information and voluntary disclosure. So at a high level, loosely at a high level, because what I'm doing here is I'm releasing actual hard data that I'm assuming the principal can't modify or manipulate to achieve her aims. And it's also related in application area to literature on rating systems design, which studies how agents, how a variety of issues of these rating systems, like how ratings impact in the entry and exit by firms, or how agents react to, do agents herd if they see all the prior information and things like that. So moving on, I'd like to get into a bit more technical detail about my work. So let me first present to you a precise model. I'm going to assume for the purposes of the talk that there are two arms, 1 and 2. This can of course be relaxed to any constant number of arms. And I will assume that there is a Bernoulli mean reward for each arm. That is, each arm A has a mean reward mu A, which means that the reward when you pull the arm is 1 with probability mu A and 0 otherwise. I'm going to assume that these mean rewards are bounded away from 0 and 1. For convenience, I will assume they are 1/3, 2/3. And I'm going to label the arms such that arm 1 is the better arm. But notice that the principal and the agents do not know this. This is just for convenience, so I can describe the settings to you. The agents are indexed by time t, and at every time a new agent arrives and chooses an arm and receives a corresponding reward drawn from the arm's underlying reward distribution. The agents can make their choice based on a signal that they receive from the principal. The signals are going to be subhistories. So for any agent arriving at time little t, the principal is going to pick a subset of past agents, capital S, and report the reward and the arm selected of every one of those past agents and the time step in which that choice was made. So this is what we call a subhistory. Our behavioral model is going to assume that agents are frequentists. So I can now explain exactly what I mean by this. The agents are going to, when they see a signal, count the number of arm pulls of each arm A in that signal, in that subhistory. That's going to be some number n sub A. They're then going to compute the empirical mean reward of the arm in that subhistory. Let's call that mu bar sub A. So that's just what is the average of all the rewards that arm A received in this particular subhistory. And then they're going to form an estimate, mu hat, about the reward of arm A. And this estimate could be anything that they want. I'm not restricting the function by how they form this estimate, except that it has to get asymptotically close to the empirical mean reward. So if NA, the number of arm pulls of arm A, is very low, I allow the agents to make arbitrary choices with respect to their estimate of the reward of arm A. They could be particularly optimistic about some restaurants and particularly pessimistic about other ones. But as they're presented with more and more evidence as to the quality of a restaurant, they have to start converging towards the empirical mean. And now that they have formed estimates of all the restaurants based on the subhistory that they were presented with, I assume that the agents are going to select the arm with the highest estimate. One thing to note about this is that I told you that the rewards mu are bounded away from 0 and 1, and for the purposes of this talk, I assume they're between 1/3 and 2/3. And this behavioral model might force agents to make an estimate that is outside that feasible interval, as I've written it on the slide, but that's actually not necessary. And in the paper, we discuss how you could alternatively assume that if the confidence interval is disjoint from 1/3, 2/3, the feasible space of mean rewards, we can just assume that the agents take the closest point in the feasible space of mean rewards. So if the agent sees a ton of zeros, they can assume that the mu is the min possible mu, which is 1/3 in the context of this talk, so long as now there's generically ties, and we need them to randomize when they see a tie. So if there's 2 restaurants that they have an estimate of 1/3 for, I want them to select between them randomly. Okay, so that's the model of behaviors, and you might be thinking, well, frequentist behavior would be particularly dumb if the principal is going to, look at me and say, I want you to go to restaurant A, and so I'm only going to show you histories in which restaurant A did well, or otherwise choose the history based on what they want me to do in the context of what's been done in the past. And that's why we also restrict the signal space of the principal. So we're not going to we're going to make further assumptions than that they simply do what we call this data disclosure policy. They're also required to choose this disclosure in an unbiased way. So there's 2 properties of that. One is the transitivity. So I'm going to assume if some agent observes a subhistory, then every agent that observes that agent also observes that agent's subhistory. This basically says that when I see that an agent made a particular choice, I know all the data that was available to that agent when they made that choice. And so I don't have to do any inference about what else they knew that I didn't know that influenced them to make that choice. Another thing is that we're going to assume that these signals are chosen ex ante. So that is, at the beginning of time, the principal commits to some information structure. Maybe on the even days, all the agents that arrive on even days see all other agents from even days, and all the agents that arrive on odd days see all other agents' histories from the odd days. Now this information structure, you could think about this, by the way, as some sort of social network, and then the agents are doing some kind of social learning in the context of this social network. And why do I care that this is fixed ex ante? And this is because, maybe if it weren't fixed ex ante, the principal could look at the rewards that the agents received. Maybe the principal wants the incoming agent in round 7 to pick, say, the red triangle arm, and looking at these outcomes of the arm pulls, realizes that it would be better that the principal could convince this frequentist agent to pill the red triangle arm if instead of showing the odd days outcomes, it showed this agent the even days outcomes. And if the principal can play that kind of game, then this frequentist behavior model is quite suspicious. And so we disallow that. And so this is just basically the discussion I just had about how these policies basically, the transitivity and the ex ante choice of the structure of the information flows means that each agent, from an agent's perspective, they're seeing the full history of an alternate reduced world in which only the agents in their subhistory exist. And so we argue that frequentist behavior is perhaps a reasonable model of behavior in such a world. We also discuss how this can be rationalized for Bayesian agents with appropriately chosen priors, but I think that's actually not the point of the paper, so I'm not going to get into that. And as I discussed, you can think about this as some kind of model of social learning. So the design goal of the principle in this paper is to choose transitive signals that minimize the regret. And that's going to be precisely t times mu1, because arm 1 is the better arm, minus the expectation of the arm rewards induced by the policy, which is going to be an expectation over the stochasticity of the arm rewards, as well as the choices of the agents. And I want to minimize this regret in the worst case over the realization of the mean rewards mu1 and mu2. So the principal fixes the policy and adversary gets to then just pick mu1 and mu2, and the principal wants to minimize this regret in the worst case over the choice of the adversary. So there's some natural first attempts you might make. One is full history, which shows that agents may herd on the suboptimal arm. That's probably not surprising if you're familiar with the social learning literature. Another first attempt might be, let's show agents no history at first. And then after we have enough agents coming in that see no history, we can start to show all future agents all existing history. And then you can show using this theorem from statistics that says that how many flips of biased coins we need to be able to distinguish them. You can show that this no history at first is going to get bounded regret if we know the gap parameter, which is how much better is the better arm. And so that's just sort of two baseline policies that you can think about. Our results are going to generalize these policies and combine them in a way to get rid of the assumption that we know the gap parameter and to improve the regret to t to the 1/2. And as I've mentioned before, t to the 1/2 is the optimal regret in the multi-arm bandit problem, even absent incentive constraints. But furthermore, t to the 2/3, which is the regret of our 2-level policy, is also optimal among what we call non-adaptive policies. Those are policies that do all their exploration up front, which means that to go beyond this non-adaptive policy, we need to do some adaptive exploration. That is, we need to explore for some time, then look at what we've learned and decide whether we need to continue with the exploration or not. So let me give you the simple policy. This is pretty straightforward. We're going to combine this full history and no history at first. So I have what I call level 1 agents, which are the full history agents. And these are, say, like every agent that comes on Monday sees every other agent that comes on Monday. And every agent that comes on Tuesday sees every other agent that comes on Tuesday, and so on. So that gives me a set of groups of level 1 agents. And this is leveraging the herding of full histories to guarantee that each arm gets sampled a sufficient number of times, which is going to be a constant number related to the number of groups in level 1. And then after we have sufficient exploration in level 1, we'll introduce level 2, which sees all of these agents and can then exploit effectively. I'm going to skip the proof of this result, but the theorem that we get is that we have regret t to the 2/3, where we have the number of agents in level 1 is something like t to the 2/3, and there's constantly paths in each group. And one thing to notice about this construction is that most agents see a large fraction of all previous history. So I am being quite informative for the agents as the principal. And the intuition as to why this works is that the level 1 agents provide enough exploration to distinguish between which arm is the better arm if the gap between their rewards is large. And if the gap between the rewards is small, then it doesn't really matter to me which arm is the better arm. Even if all agents pull the suboptimal arm, I'm still get low regret. So you can think about the level 1 agents as providing the exploration in this construction, and the level 2 agents as providing the exploitation. And as I discussed, to improve upon this, we need to do adaptive exploration. And so let me discuss briefly how I'm going to perform adaptive exploration, even when agents, I'm confined by agents' incentive constraints. So I'm going to start with a 3-level policy, which is going to improve a bit, but still not be optimal. And then we'll discuss how to move to the optimal, how to converge to the optimal policy. So the 2-level policy, for those of you that know multi-arm bandits, basically mimicked a well-known algorithm in practice. These next two policies that I'm going to introduce are not so common as policies in the multi-arm bandit literature because they perform a limited number of predefined exploration rounds. So the level 3 policy performs either 1 or 2 exploration rounds, whereas the 1-level policy had just 1 exploration round. So the 3-level policy is going to make many copies of the 2-level policy and then combine them all at the top. Why is this a good idea? Well, as before, the level 1 agents are doing exploration, and the level 3 agents play the role of the previous level 2 agents and do exploitation no matter what. But the idea is that these middle level agents are going to exploit if there's a clear winner, and otherwise they're going to explore more. And this is without us telling them to do so. How do we guarantee that this happens? The idea is that the level 1 agents are going to, provide some exploration. If their exploration was sufficient to distinguish the better arm, then all level 2 agents are going to exploit. If their exploration was insufficient to distinguish the better arm, then some of the groups in level 1 are going to have histories that suggest the, say, triangle arm is better. And other groups in level 1 will end up with histories that suggest that the circle, I forget what shapes I was using, the other arm, the circle arm is better. And so you're going to get, each arm is going to get lucky in some of the groups if the level 1 didn't have enough power to distinguish them. And then level 2 agents are going to provide additional exploration in that case. So the level 2 agents that are group aggregators of a level 1 group in which the triangle arm got lucky are going to provide additional exploration of the triangle arm. And level 2 agents that are group aggregators of level 1 groups in which the diamond arm got lucky are going to provide additional exploration of the diamond arm. So I'm going to skip the proof sketch, but that's the basic idea. And in order to extend this to multiple levels, so the proof sketch, it's a proof by cases as before, except that now I can have the level, before I switched, I had a case based on whether the gap between the better arm and the worse arm was large or not. And in the 3-arm case, I have a new level, a new gap. So I'm sort of refining down the gaps that I can distinguish because of this intermediate level that I introduced. So to get finer and finer gaps, I need to create more levels. And the idea of the L level construction is that I'm going to create a level, little l, for any potential gap, capital delta. And this level's job is to do additional exploration if the previous levels didn't have sufficient exploration to distinguish that gap delta. First attempt that you would naturally consider based on what I've described so far is to make many copies of the 3-level agents and connect them with 4-level agents and so on, and grow out this big L-ary tree, this L-level M-ary tree. And this indeed provides refined exploration, but it does so at a massive cost because, of course, there's way too many level 1 agents in this construction. There's exponentially many level 1 agents, and each of those agents has potentially high regret. And so in order to pull this off, we have to reuse samples by, basically we need to reuse information in a way that doesn't pollute the information. So I still want to keep enough independence that experiments can be independent, but I need to reuse samples such that I don't get this exponential growth in the level 1 agents. And so we have a way to do this. You can read about it in the paper. And with this construction, we can prove that you get regret that approaches t to the 1/2, which is the optimal regret of multi-arm bandits. So in conclusion, I have several, I guess the main results. Let me first remind you of the main results, which were that we can get optimal regret with this selective data disclosure, this model in which we have frequentist agents and have to offer the agents unbiased subhistories of past arm pulls. We like this model a lot as it, loosely speaking, relaxes the commitment assumption and relaxes the rationality assumption, and is robust both with respect to the need for prior assumptions about priors, and also in some small ways with respect to the modeling parameters themselves. And nonetheless, we get optimal regret. And the main ideas of the policies we introduced, I think the most actionable one is that it's a great idea to use focus groups of agents to get natural exploration of arms. That happened in the level 2 policy. In the level 3 policy, you can add group aggregators to refine exploration. And in the L level policy, we saw that you needed to reuse information in order to get optimal regret rates. So thank you for your time.
Awesome. Super cool. Also love watching the result hierarchy transforms sort of as you go up in levels. Very, very neat. We have a couple of minutes for questions before the next talk, and I might, use my position as the moderator to ask a question immediately. Could you maybe tell us, like, sort of take us back to the mapping that sort of gets us to the application? So, like, how do we use these types of information design results in practice?
Yeah, so the information design, so the application that I was using as motivation throughout this talk was Yelp, right? So Yelp is trying to get people to do sufficient exploration of restaurants. And I firmly believe that this is a problem Yelp thinks deeply about, although I don't consult for the company. But you can see this, for example, they have a cashback program where they're trying to do this other thing that I mentioned of paying people to explore. Or perhaps that's one objective of the cashback program, you could argue. But what this is saying is, like, another way you could do this is introduce some randomization in what reviews people get shown, or in some way introduce some heterogeneity in what reviews people get shown. And this can be very useful for inducing exploration, and is particularly effective for short-lived agents. I mean, some people always complain, what happens if you and your partner see different reviews? You might get suspicious. But, like, if these are short-lived agents without much cross-communication, this is going to naturally induce me to go to Arturo's and somebody else to go to whatever the other pizza restaurant, Spring Street Pizza. Now they get to learn about both of them. And another thing is that, the model suggests that these frequentist agents, maybe this is a reasonable behavioral assumption, which suggests that Yelp, as it already is, should be showing me aggregate statistics of the form, what is the empirical mean reward, and what is the number of reviews of each restaurant. So those are two concrete things that Yelp should do. It should show different people, different histories, to maybe not, they don't have to be completely disjoint because, you're moving from theory to practice. But if it has some kind of heterogeneity in the histories, it'll induce some amount of exploration, and then it should offer aggregate statistics.
Super cool. Thank you. Awesome. They should hire you. Or I guess maybe that might be a conflict of interest because you're also employed by a different company. But they should ask you to advise them. Cool. Any further questions? As people know, we can perhaps to the speaking rest only audience. People in the audience with questions, please put them in the question answer or in the chat. Going once. Going twice. All right, sold. So thank you, Nicole. That was totally awesome.
Thank you, Scott.
And we will, I will literally see you soon, but yeah.
Sounds good.
QED.